So here's our main information right up here at the top. A matched pairs experimental design takes two forms. The experimental units are matched to produce more precise results than simple randomization. Or number two, each experimental unit receives both treatments and is compared to him or herself. Now hopefully you understand the idea behind number two. For example, if we wanted to test out what could we test here? Two different types of diets. We could put you on diet A for 6 months and then put you on diet B for 6 months. And then we could measure, how much weight did you lose on diet A versus diet B? If they were about the same weight loss, we'd say, well, there really is no difference between the two diets. If one diet produced greater results than another diet, we could say, hey, this diet definitely worked better for you than it did for maybe other people. Now, the first one where they said the experimental units are matched to produce more precise results than simple randomization. What that means is we have, say, two individuals, you and someone pretty similar to you in terms of specific characteristics, and it depends on the context of the problem. So, for example, if we were talking about weight loss, we would want to match someone that is about the same build, about the same height and weight, and maybe what other factors you would consider with weight loss. Maybe activity, like exercise level. You don't want to have someone that exercises a lot matched up with someone that doesn't really exercise a lot, because that could be a lurking variable, the amount of exercise, because it differs. So you'd want to have two people that are maybe about the same height, about the same weight, and they exercise about the same amount as each other. And then we could give one of those people diet A and the other person diet B. And that way we could compare them to each other like they're kind of like the same person, but they're really not the same person. So the type of match pairs design you'll see more of will be more of this second one, where we're going to take each person and each person will get multiple treatments, and then we'll just compare each person to him or herself. So we're going to look at a couple of examples here. The first example says a manufacturer of boots plans to conduct an experiment to compare a new method of waterproofing to the current method of waterproofing. The appearance of the boots is not changed by either method, so you can't tell if the waterproofing solution has been applied to the boots or not. The company recruits 100 volunteers in Seattle, where it rains frequently, to wear the boots as they normally would for 6 months. At the end of the 6 months, the boots will be returned to the company to be evaluated for water damage. So part A says, describe a design for this experiment that uses the 100 volunteers. Include a few sentences on how it will be implemented. Now, with my 100 volunteers, you might think, all right, what if we take 50 of them and we give them the new waterproofing method, and we take our other 50 volunteers and give them the current waterproofing method, and then let's compare. Well, people will tend to maybe wear boots out more than other people do. So what we could do is use a matched pairs design, and that way we take away that factor. So each person gets one boot of each kind. One person gets maybe their right boot is the new method and their left boot's the old method. Okay? So we could label our subjects 1 through 100. And since we only have 100 people, we could use the HAP method instead of using our calculator or the random number table. So this is just one scheme here. Okay, there are many different possibilities. So I'm just saying let's pick 50 numbers or names out of a hat, and the first 50 people will be in group 1, and the other people will go into group 2. And then I could say people that are in group 1 will get a right treated boot and a left untreated boot. Or we could say a right new treated boot and a left old treated boot. And then group 2 gets the reverse. And you might ask, well, why does it matter that group 1 gets the new waterproofing on their right boot and group 2 gets the new waterproofing on the left boot? Why would that make any difference? Well, if you would look at your shoes, if you're right-footed, you're probably going to wear out the right shoe more than your left shoe. You put more stress on whatever foot that you're dominant with on that shoe. So people that are right-footed versus left-footed, it really depends on how much wear they're going to put on those specific shoes. So maybe there's going to be a difference between a right shoe, a right boot, and a left boot. So that's why we have group one. They all get the new waterproofing treatment on their right boot, and all group two people get the waterproofing on their left boot. So if people are right-footed dominant, then people in group one should have more wear on that one. But chances are there's going to be some people in group one that are left-footed dominant. So we'll see, as a mixture of right versus left-footed dominance, how just the right boot is affected. And the same thing will happen on the opposite end with the second group. Since the left boot will be the one that's treated with our new waterproofing, then we'll see how right and left-footed dominant people, respond to that. And then once we're done, the subjects are going to wear our boots for 6 months and then return them to be inspected for water damage. Part B asks, could your design be double blind? And if you think back, double blind, just jump back here, double blind meant that neither the subjects nor the people who have contact with them know which treatment the subject received. So could our design, and really should our design, be double blind? And absolutely. I mean, the people given or receiving the boots really shouldn't know which boot has the newer waterproofing method. If they did know which boot had the newer waterproofing method, they might try to really test it out and splash it more in the water to see if it really holds up. If people knew that a certain boot had the old waterproofing method, they might try to avoid puddles or big water scenarios because they know it's not the new method of waterproofing. And when the people receive the boots after the 6 months, they shouldn't know which one has the new or the old one because they could, inadvertently sway the decision of which waterproofing method is superior. So nobody should know except for a third party that kind of overlooks, kind of like Big Brother, if you will. Only Big Brother should know which subjects were receiving which boots and vice versa. Now the other type of idea is called a block design. And this is going to sound really familiar because a block design is kind of like a stratified random sample. But there's a big difference here. A stratified random sample deals with sampling, with selecting people. A block design is a type of experiment. It's not how you are selecting the people. So they are very similar to each other, but there's that key difference of sampling versus experimenting. Okay? So it says a block is a group of experimental units or subjects that are known before the experiment to be similar in some way that is expected to affect the response. In a block design, the random assignment of the units to the treatments is carried out separately within each block. So when you look at a block design itself, it looks like you're doing the experiment multiple times within each block, within each strata, if you want to kind of think of it that way. So again, instead of stratas, we have blocks. So the first example here says the progress of a type of cancer differs in men and women. A clinical experiment to compare 3 therapies for this cancer therefore treats sex as a blocking variable. If men respond differently than women, then we obviously want to separate men from women to see if men respond differently to a certain therapy than women may respond differently to a different therapy. 2 separate randomizations are done, one assigning the female subjects to the treatments and the other assigning the male subjects. Note that there is no randomization in making up the blocks. The blocks are made by gender. The randomization comes into play when they split each gender up into the 3 treatments. Okay, so typically when we start to split up our groups in a completely randomized design and in a matched pairs design, the first thing we do is the random assignment. But notice here are all of our subjects. First we split them up into the blocks, men versus women. And then once we have all our men together, now we randomly split them up into groups. And the same thing for the women down here. Once we have all the women together, then we randomly put them into groups. Okay? Again, you're not going to do the random assignment at first. It's not like you're randomly putting all the men together and all the women together. That makes no sense that you randomly do that. You're just saying all men over here, all women over there. Now let's introduce randomization to this. So this says, label the main features of the randomized block design. Well, I've already got the picture set up here. And we're just going to label where does the randomization come into play, then the groups, the treatments, etc. It says list the group sizes. There are 180 subjects total, 30% of whom are male. Okay, so number one, we have our 180 subjects here. Now, how many men and how many women do we have? It's not 90 and 90 because they didn't say 50% are male. It said 30% are male. So if I have 180 subjects and 30% of them are male, well, that gives me 54 men. And if I have 54 men, then I have 126 left over out of my 180. That must be women. So here are my blocks that I've split up because it says two different types, or a type of cancer differs in men and women. Therefore, I'm splitting up my blocks by gender. So there's my 54 and 126. Now from there, I randomly split up my 54 men among 3 treatments. So 54 divided by 3 is 18 per group for the men. 126 divided by 3 gives me 42 in each group for the women. Is it okay that there aren't as many men as there are women? That's fine. Okay, in real life, it's going to be nearly impossible to have 50-50 or even amounts of individuals per group or per block. That's very rarely going to happen realistically. Okay, so then my group 1 random assignment of men, they're going to get therapy 1, group 2 gets therapy 2, group 3 gets therapy 3. And in the end, I go and look at, well, let's look at survival rates after these therapies. How many men, what percentage of men survived after getting therapy 1? How many against therapy 2? How many at the end of therapy 3? And then I can decide for men which therapy did best. Okay, maybe therapy 1 was the winner for men, that we had more men survive with therapy 1 than 2 or 3. And then I come down here for the women, and I do the same thing with my 42 groups of 3 sets of women here, and I give them therapies 1, 2, and 3, the same therapies 1, 2, and 3 as I did for the men. But maybe therapy 3 ends up being the best therapy for women. More women survived with therapy 3 than 1 or 2. Okay, and this is why I decided to split my genders, because I had a feeling before the experiment started that men might respond differently than women. Now, let's say you do this whole experiment, but you don't split up by gender, and you just take your 180 subjects and you split them up into 60, 60, and 60 for therapies 1, 2, and 3. Well, then you might not find the same result. Okay, maybe therapy 2 ends up being the winner for men and women combined. So there's that lurking variable of gender that we have ignored. And then if you go, wait, maybe men and women will respond differently. But if you've already done the experiment, you can't at that point go back and say, well, I should have done this. That's not block design anymore. You have to knowingly know before the experiment that there's going to be a difference between whatever variable that you're blocking by, whether it's gender or age or income level or education level. You have to block before you experiment. Otherwise, it's not really fair that you go back after the fact and then split them up. That's very unethical, if you will. Now, one thing that I see students do a lot of is they'll take the men survival rate and the women's survival rate, and then they come back and say, let's compare overall. Well, you don't want to do that overall. The main reason why we split them up into blocks is because we thought there was going to be a difference. So why would we then compare our two things as one at the very end? We don't want to compare our individual blocks at the very end. It really makes no sense. You're splitting them up at the beginning of the experiment because you know there's a difference, so it makes no sense to compare your different results at the very end of the experiment. That defeats the whole purpose of blocking to begin with. So there is no end comparison between all your blocks. You just leave them as separate blocks. So it looks like one big experiment that you are doing multiple times, one for each block.